Good afternoon, everyone. I'm very happy to be here. First of all, I would like to thank very much the Greek and the Romanian societies of soil foundations and geotechnical engineering for hosting us here today. My presentation is on the verification of seismic risk models using observed damage from past earthquake events. And it is a part of different works we have been doing in the last few years in our research unit in the Civil Engineering Department of Aristotle University of Thessaloniki, with the active involvement of a lot of colleagues whose names you can see here on the slide. Dr. Stephanie Apostolaki, who successfully defended her PhD thesis yesterday, Emeritus Professor Kyriazis Spitilakis, Professor Dimitris Spitilakis, Professor Sortsinidis from the University of Thessaly, and our colleagues from Turkey, Dr. Karahan and Professor Gokçeoglu, who helped us a lot with providing very useful data, as you will see in the following. I will start with a short introduction. The main topic of my presentation is the seismic risk. And with seismic risk, we mean the potential impact on the built environment and on people's well-being from future earthquakes. As most of us probably already know, risk combines information on the hazard, which is the potential for an earthquake, exposure, which refers to the assets and the people that are exposed at the earthquake risk, and vulnerability, which is a measure of the proneness of the structures to damage. In the last few years, we have seen that there are a lot of new openly available seismic risk models. For example, in Europe, in 2021, the first ever European seismic risk model was released. It's called the SRM20, and it is a part of the global earthquake model, which we probably all know as GEM. Specific components of these risk models can find a very useful application in the rapid damage assessment. That means that they help us to rapidly have a first-order estimate of the damages after an earthquake occurs. So it makes perfect sense that we need to verify and also calibrate these models, and the best way to do it is through a comparison with what these models predict with observed damage. And this is what I will try to present in this presentation. So first, I will say very few words on the Karamanmaras earthquake sequence of 2023, as Professor Garini already explained all this in great detail. And then I will focus mostly on the seismic performance of tunnels during this earthquake sequence and how we used this information to verify available seismic risk models for tunnels. And then in the last part, I will present also some results on the verification of available seismic risk models for residential buildings, which is something that is widely used in the framework of rapid damage assessment. This map, we have seen it in also the previous presentation. The sequence consisted of two main events, which happened with only 8 or 9 hours distance. The first is the Pazarzik 7.7 magnitude event, and the second is the Elbistan 7.6 magnitude event. I have to say here that these magnitudes are slightly different than the ones Evangelia mentioned earlier, as they are the magnitudes that as they are given by the Turkish network AFAD. So the first event was the 7.7 event with a depth of 10 kilometers. It was because of the rupture of around 280 kilometers fault in the East Anatolia fault zone. It was recorded by around 380 accelerometric stations, which we can see in the figure on the left. The PGA values were very high. For example, there was a PGA of around 2G in Pazarzik. And on the right, we can see the shake map, which is a map of the spatial distribution of a specific intensity measure. In this case, it is the PGA, the peak ground acceleration. And these maps are produced very shortly after an earthquake. For example, in this case, if the first version of the shake map was available only 10 minutes after the event, and they are produced using not only the data that are available from the stations, but also a community-driven did you feel it system, where everyone who feels the earthquake can answer a simple questionnaire, and this information is then converted to intensity and the PGA or other intensity measures. The second event was the Elbistan earthquake. It was due to the rupture of a 140-kilometer long fault. It was also recorded by a lot of stations, and again we can see here the PGAs as they were recorded by AUTH on the left, and on the right the USGS shake map. A few words on these shake maps as we widely use them, as you will see in the following. I also said earlier that these are available very few minutes after the event. So for the first earthquake, we had a shake map 10 minutes after the event, while for the second Elbistan earthquake, we had the first shake map 20 minutes after the event. But these shake maps are updated very often as new data become available. For example, when information on the rupture of the faults becomes available, this is something that adds information and improves the available shake map. So we have 19 versions so far for the shake map of the first event and 12 versions for the shake map of the second event. Another thing that we need to stress here is that these shake maps use some quite rough models for the local site conditions for the VS30. For example, the USGS has a global VS30 map, the global mosaic as they say it, which consists of VS30 which are correlated with proxies such as is the slope of the terrain or the geology, while in some other locations where there is a better information on the VS30, this is adopted in this model. For the case of Turkey, these models are, I think, completely proxy-based. So this is something that we should keep in mind for a potential accuracy of these shake maps. This is the area that was affected by the earthquake. It consists of 11 provinces, which cover an area of 110 square kilometers. You can see here with the stars the epicenters of the two events, and with the red lines the ruptures of the fault that caused these two events. And I will now continue with the effect that these two earthquakes had on the tunnels in this area. So the aim of this part of my presentation is to report and describe the observed damages to numerous tunnels that were located in the affected area. We also try to investigate the main causes of the damages that were observed in terms of typology of the tunnels, ground conditions and depth of the tunnels, distance to the faults, as well as ground motion characteristics, for example, the level of PGA. And finally, we try to use this data that we have on the observed damages to make a verification of existing fragility models that we have for the case of tunnels. So let's see what kind of tunnels we have in the affected area. The affected area of the 11 provinces that we saw earlier has a total of 87 tunnels in the affected area. These tunnels are shown on this map with the small black dots. I hope you can see them. These dots indicate the midpoints of the tunnels. As we know, the tunnels have a specific length, but in this work that we did, we simulate each one of these tunnels with a single point, which is representative of the midpoint of its length. Here we see again with the black dots the tunnels, and these tunnels are now superimposed on the shake maps of the two events. So we see here on the left the shake map of the first event. I also have a pointer here. Okay, so this is the shake map of the first event, this is a shake map of the second event, and what we can immediately see is that there are some tunnels which were unfortunately very close to the ruptures that resulted in these two events, both for the first event and also for the second event. And as we will see in the following, the distance of a tunnel to the rupture is something that significantly influences its response. A few words on the type of tunnels in the affected area. It seems that tunnels in this region have been constructed mainly in two periods. There is a set of tunnels that were constructed before 1975, when the first Turkish seismic code was widely adopted. And then there is another set of tunnels which were constructed after 1995, when the TEC 1998 regulation was in force. In 1912, we have a lot of railway tunnels that were constructed. These tunnels are like the one that is shown here in this photograph, and these are mainly masonry-lined arched structures with a single lane. Between 1927 and 1937, railway tunnels of various types, either from concrete, masonry, or hybrid, were constructed in the framework of the Fevzi-Passadi-Diyarbakir railway project. While in the last 3 decades, we have a lot of RC tunnels, which are either in highways, and these are either 2-lane or 3-lane, or in railways, which are either 1 or 2-lane, like the ones that we see here in the pictures at the bottom of the slide. Regarding the sections, we have a big variety of tunnel sections. So there are either cut and cover rectangular sections. We also have egg-shaped tunnels. We have these arced tunnels. We have these horseshoe sections. And luckily, we were able to develop an exposure model, an inventory for all these tunnels, thanks to a field survey that was conducted by 2 of our Turkish colleagues, Professor Gökçeoğlu and Dr. Karahan, who did a field survey after the end of the earthquakes, and they were able to gather a lot of information on the tunnels. So we built this inventory, which for all the 87 tunnels contains information which describe the typology of the tunnels. And when I say typology, I mean a combined information on the year of construction, the material of the lining, and the type of the section. We also have information on the geometry of the tunnels, the length, the width, the height, and the depth. And we also try to gather some information on the local ground conditions at the locations of the tunnels. So, from our Turkish colleagues, we have an information on the geological strength index, GSI. This refers to an average value of GSI across the length of each tunnel. And we also collected some information on the VS30, which again is a VS30 that is obtained through correlations with proxies, and these proxies are the slope and the geology. Finally, we calculated for each one of the tunnels the distance from the 2 faults. This distance refers to the distance between the midpoint of each tunnel and the rupture, the closest distance. And we also have the PGA, which we obtained from the shake maps of the United States Geological Survey, USGS. Finally, maybe the most important information is on the damage level. So we have 4 categories: no damage, slight, moderate, and collapse. So the inventory that we developed has this kind of structure. For each tunnel, we have an ID. And then we have the typology, which combines the year of construction, the material, and the type of the section. We have this information on the geometry of the tunnel. We have the GSI, the distance from the 2 ruptures, the PGAs, and of course the level of damage. And all this data, all this information, as well as the results of the analysis that I will present later, are available for anyone who is interested in an open Mendeley data repository, and I give you here the link with which you can access all this data. A few words on the typologies of the tunnels. We can see here that regarding the material, out of the 87 tunnels, the 51 are concrete. There are 28 masonry and 8 hybrid tunnels. Regarding the construction period, as I said, there are some tunnels that are new, on the top, and some tunnels that were built prior to the 1970. And all this information is combined here on this map, where with the different colors we present different typologies. For example, the red dots refer to some old tunnels, while the greenish dots refer to some more modern tunnels. Regarding now the depth, we have here a table which classifies the tunnels according to the depth. For example, we have around 30 tunnels that are shallow with a depth less than 10 meters. We have around 25 tunnels with an intermediate depth and 30 tunnels that have a large depth exceeding 40 meters, or even some tunnels are at a very high depth, greater than 200 meters. Now, regarding the GSI, the Geological Strength Index, which is a rock mass characterization parameter, we can see that there are around 30 tunnels that are located in high GSI regions, let's say above 40, but there are also quite some tunnels that are located in lower GSI, in areas with lower GSI values. Higher GSI generally corresponds to greater strength, so we expect that this might have some impact on the response of the tunnels. Now, regarding the observed damage, we can see here this table where the first thing that we see is that out of the 87 tunnels, 77 exhibited no damage at all. So we had a very good performance, overall performance of the tunnels in the area. There was only one tunnel that collapsed. There were two tunnels with moderate damage and 7 tunnels with slight damage. The only tunnel that collapsed is the tunnel with ID 5. It's somewhere here in Adiyaman. And this collapse was due to fault crossing. So this tunnel crossed the fault that ruptured, and this resulted to the collapse of a big part of this tunnel. For the remaining tunnels with the moderate and the slight damages, this damage was mainly on the lining of the tunnels. Let's see now, not a lot, few pictures from the damages. So this is the tunnel with ID 5. It's the only tunnel that collapsed. Around 150 meters of the tunnel collapsed due to fault crossing. This is a tunnel that is a part of this Malatya-Narli T3 railway, and we can see that it is a masonry tunnel that was constructed in 1930, and we also observe that it is located in quite low GSI region with a value of 15. Regarding the PGA, we can see that this tunnel had a PGA of around 0.66 due to the first event, and 0.28 due to the second event. Again, these values refer to the midpoint of the tunnel. The actual PGAs could be higher at the part that crossed the fault. This is the tunnel with ID 16. It is a railway tunnel at the Tropakale Meyedan-Kebges T14 railway. This tunnel had a slight damage on its masonry lining. Again, it is a tunnel that was built in 1930. It is a hybrid tunnel. And we can see again that this GSI value here is also quite low. It's in the same, more or less, region as the tunnel that we saw in the previous slide. This tunnel had a higher PGA due to the second event, while it was lower due to the first event. Next, this is the tunnel with ID 64. It is the Malatya-Gaziantep-Erkenek highway tunnel. This tunnel experienced moderate inner lining damage, and what is surprising is that this is a reinforced concrete tunnel that was constructed in 2017. So we observe here that the damages were not only observed in the older masonry tunnels, but also in some new, more modern structures. So here we try to visualize in a better way the observed damages. So what we plot here, we plot the PGA. These PGAs are obtained from the shake maps. So the figure here is from the first event, and this is from the second event. So we plot PGA versus closest distance to the rupture. And each point here represents a tunnel. And these colors, I don't know how this red can be easily discriminated from this orange. The colors indicate the level of damage. So the tunnel number 5, this should be a red triangle, represents the only tunnel that collapsed. So, as we said before, this tunnel number 5, was a masonry tunnel that was constructed in 1930. We also see that this tunnel is located very close to the epicenter of the first event, but also not so close, not so far, from the epicenter of the second event. We can see that the PGA was quite high due to the first event, around 0.66, and lower due to the second event. And one could possibly say that this tunnel collapsed probably due to the first event, as it is much closer to the fault of the first event, and the PGA is also much higher. Finally, I have to say here that the type of symbol here represents the GSI value. So here we can see that this is a triangle. This means that it has a low GSI, and this low GSI might have contributed somehow to the collapse of this tunnel. Okay, here we have the same figures as before, but now the different symbols do not represent the different GSI values, but they represent the period of construction. So what we see here first is that we have a lot of triangles. Triangles means that we have a lot of old tunnels, which are quite close to the rupture, but they are red. This means that they had no damage. And this means that several old tunnels, even though they were very close to the fault rupture, performed very well. We also see that the newer tunnels that are represented by the rectangles also seem to have a good performance. Now, there are still some examples like ID64 and ID46, where we see that we have modern tunnels which still exhibited some degree of damage. For example, this had a moderate damage and this had a slight damage. Specifically for the tunnel with ID46, this damage may be attributed to some very low local GSI values that are found at some places along the length of the tunnel, although the average GSI is not that low. So some preliminary observations from the previous plots is that only 10 out of the 87 tunnels collapsed. From these 10, not collapsed, had some damage. Out of these 10 tunnels, only one collapsed. And what seems to be the controlling parameter is the proximity to the faults, while the PGA, the ground conditions, the age of construction, and the typology seem to play also a complementary role. The next thing we try to do is to try to make a first-order estimate of how rare the PGA levels that were experienced by the tunnels might have been, in order to see how much these locations were affected by the earthquake. So, in order to do this, we performed a probabilistic seismic hazard analysis, a PSHA, in order to obtain, for each one of the locations of the tunnel, a seismic hazard curve. To do this, fortunately, we have a lot of tools available. For example, we have the OpenQuake engine. It is an open source software that performs probabilistic seismic hazard and risk analysis. We also have the European Seismic Hazard Model, HSSMGE, which provides a very good source model, seismogenic source model, and some appropriate ground motion models for the area. We also have some information on the local site conditions, a proxy-based VS30 model from the European Seismic Risk Model, ESRM20, and we can use all this to model each tunnel as a single point and then derive for each of the tunnel a seismic hazard curve. So, from this probabilistic seismic hazard analysis, we can see here two maps. This map shows the spatial distribution of the peak ground acceleration for a return year of 500 years, and the map here shows the PGA distribution for a return period of 2,500 years. These are not PGAs from the earthquakes, these are PGAs that resulted from the probabilistic seismic hazard analysis. And the first thing that we observe is that alongside this area, which is where the fault rupture of the first event happened, we have, of course, higher values of PGAs compared to the tunnels that are further away. And this is because, of course, this is the East Anatolian fault that is included in the seismogenic source model that we used, so higher PGAs are produced here. And the same is also for the higher return period, the same impression that we get. Now, in order to compare the PSHA results with the values of the shake maps, we used a subset of 65 out of the 87 tunnels in total with quite high VS30, higher than 500 meters per second, so as to eliminate any effect of the very low VS30s. And we extracted from the shake maps the PGA values for the two events, and then we used the seismic hazard curves that we obtained from the PSHA to see what return period corresponds to the specific PGA levels of the shake maps. I have to stress here that these return periods refer to the exceedance of specific levels of PGA at the selected sites and not to the occurrence of an event of the specific magnitude. So it's not a return period of the magnitude, it's a return period of the selected given levels of PGA. An example is shown here. This is the seismic hazard curve that we calculated from the PSHA for the tunnel that collapsed, the tunnel with ID5. The PGA from the first event was 0.66, so we go here, we find the PGA of 0.66, we go up, and we see at which point this line crosses the hazard curve. This is the annual probability of exceedance. Sorry. I don't know. I will try to use the pointer here. Okay, so this is the annual probability of exceedance, and this refers to a return period of 680 years. This means that the specific level of PGA corresponds to this type of return period. For the second event, the respective return period is 156 years. So if we plot now these return periods, we can see on the map on the left the return period that correspond to the PGA levels of the first event. So we see here that we have return periods ranging between 40 and around 2,700 years. Of course, the points that are closer to the fault have higher return periods, while for the second event we have a return period range between 18 and 4,000 years. With this gray shaded area, we have plotted here a buffer zone of 20 kilometers so that we're able to see better which are the locations of the tunnels that are closer to the rupture of the two events. So the closer we are to the ruptures, the higher, of course, these return periods. Yes, so in these two plots, we plot the distribution of the calculated return periods with respect to the closest distance to the rupture. With the red dots, we have the tunnels that are within this buffer zone of the 20 kilometers, while with the blue colors, we have the tunnels that are outside this buffer zone. So we observe here what we were expecting. The return period decreases as the distance to the fault increases, and this is something that is evident for both events. However, we see here that for the tunnels that are located close to the rupture, there is a significant scatter of the return periods that we calculated. And this is something that could be attributed perhaps to the very strong near source effects that were observed in this first event, which is something that we cannot easily account for in a conventional PSHA, which we used to get these return periods here. So then, the final part of this work is to try to use all this very important information on the performance of the tunnels to try to verify some existing fragility models. To do this, we perform a scenario-type seismic risk analysis, again with the OpenQuake engine, in order to estimate the expected damages to these tunnels, using for the seismic demand the latest shake maps of the two events, and 3 different types of fragility models, 2 empirical, the HSSMGE and the ALA, and 1 analytical. Okay, now it's working, which is the one that was developed by Andreotti and Lai in 2019. And if we compare the estimates of the damages with the actual observed damages, we can somehow understand if these fragility models are working or not. A few words on the fragility models that we used. The American Lifeline Alliance 2001 and the HSSMGE 2004 are 2 very widely used fragility models for tunnels. These are based on expert judgment or statistical process of reported data. The ALA takes into account the type of construction, so here it says good quality or poor average quality, and it has a heavy damage state, while the HSSMGE fragility model has no heavy damage state, it has only slight and moderate, and it uses as a parameter the type of construction, so we have a model for bored drilled and a model for cut and cover. These are both PGA-based models. While the next model, the Andreotti and Lai, it's a more recent model. It is based on nonlinear dynamic analysis of various tunnel ground configurations. These models are both PGA and PGD based. In our analysis, we use the PGA based model. And we can see here that they take into consideration the depth of the tunnel, which is something that is very useful for us, as we had tunnels of different depths. Again, here we have only the minor and the moderate damage states. So here we see a table which summarizes the results of our analysis and compares these results with the observed damages. So the column here, the last column, is the actual observed damages. And what we see here, let's first take a look at the moderate and heavy damages. We can see that the HSSMGE results in 13 moderate from the first event and 7 from the second. The ALA respective numbers is 11 and 6. The Andreotti and Lai is 17 and 10. The actual moderate and heavy damages were only 3 tunnels. This shows us what? It shows us that all fragility models overestimate the number of tunnels with moderate or heavy damage. However, if we look at the slight damages, we can see that the comparisons are fairly good. We have 6, 9, 6 compared to the actual 7 tunnels that actually had slight damage. So we can see that depending on the damage state, some models behave better, some models behave worse. However, this type of comparison between what we estimate from the fragility curves and what was actually observed is something that is very challenging, because there are differences in the way the damage states are defined. There are differences in the number of damage states that are used. There is the actual subjective nature of characterization of the damage. There is the fact that we had 2 events which happened very closely one to another, so it's not easy to say if the damage was due to the first or due to the second event. And of course, the fact that we represent each tunnel with a single point is something that adds to the uncertainty of the whole problem. So we decided to use another damage metric, which is the probability of damage of any level. And this is what, if we have, for example, these 2 fragility curves, the green is for the slight and the orange is for the moderate damage, we use the sum of these 2 probabilities, slight and moderate, and this means the probability that the tunnel will have any degree of damage. So here we plot these probabilities of damage. This figure is with the HSSMGE fragility model. The USGS shake maps are always used in this type of analysis to represent the seismic demand. And we see here what I have shown a lot of times, that the tunnels, that the probabilities are higher at the tunnels that are near the fault ruptures. And this is represented in both figures. Now, in order to compare our analysis with the observed damage, we have to make some kind of assumptions. So we assume two thresholds. The one is a 20% threshold, below which we expect to have minimal damage. This is a threshold for the probability of any damage. And a 50% threshold, for which we assume that above this, there is a higher probability of severe damage. And here, in this plot, I don't know how easy it is to read, we have on the x-axis the ID tunnel. So we have a single bar for each one of the tunnels. The dots represent the probabilities of damage that we calculated from the analysis. We have different colors for each one of the different fragility models. So the black is for Hazus, the blue for ALA, and the green is for the Andreotti and Lai. And we also have these vertical bars. So this red bar, for example, it indicates tunnel number 5, which is the tunnel that collapsed. The yellow lines represent the bars represent the tunnels that had slight damage. The orange bar represents the tunnels that had moderated damage. And what we see here is that based on the results of our analysis, all these dots that are above this 50% threshold, so that are within this red shaded area, these are tunnels that we would expect to have significant damage. And we can see that for the first event, we have around 17 tunnels in this red shaded area. Due to the second event, we can see that the tunnels that exceed these 50% threshold are around 10. So again, we have the same result that we have before, that these models tend to overestimate the number of tunnels that experience some important damage. However, what is evident from these figures is also that this approach can capture the actual tunnels that experienced, in fact, the damage. For example, we see here that this is the red bar, which represents the tunnel that failed, that collapsed. This is captured by our model. This tunnel that had moderate damage, it is captured by our models. Also here, all these yellow bars represent tunnels with slight damage. These are again captured by our model. So we predict expected damages, but we identify also the tunnels that actually experienced any degree of damage. So, to conclude on the tunnels, despite these very strong ground motions, we can see that the observed damages were quite limited, and this supports the general opinion we have that the underground structures perform better than above ground structures. It seems that the distance to the fault and the intensity of the ground motion are the most important parameters. And if we had to propose a threshold for the appearance of slight damage, at least, we could say that a distance less than 20 kilometers and the PJ higher than 0.2 G could be some perhaps good values for these thresholds. Finally, the fragility models are generally conservative, but they can provide a very useful first-order estimate of the damages that we should expect. I will move now to the last part of my presentation, which is on the residential buildings. Again, I will use the Karaman-Maras earthquake sequence as an example. Similar works. We have done similar works also for Greece, for Thessaloniki, using the 1978 earthquake, as Dimitri showed in the first presentation, and also for Athens, but these are not in my presentation. So, in order to do this, we try to apply as much as we can open data and open software, which are available shortly after an event, so that we can see how all these models can be used for the rapid damage assessment. So we used different versions of the USGS shake maps. We used the exposure model for Turkey that is provided by the European Seismic Risk Model. This is at administration level 1. It is at province level, so it's quite a coarse exposure model. We use the fragility models for residential buildings, again by SRM20, and we use the OpenQuake engine software. The building exposure model in this territory of 11 provinces has around 1,300,000 residential buildings. The model is at administration level 1, so it means that each province, the buildings of each province are aggregated at a single point, and this point is the density weighted average centroid. And the building classification that is used is the very well-known GET for all building taxonomy, which is adopted by the global earthquake model, ESRM20, and in general all the modern risk models. These are some representative fragility models that we applied by SRM20, and I will move straight to the results, where we can see here for the 11 provinces the estimated number of buildings per damage state. So we have the no damage, the slight, the moderate, the extensive, and the complete. We can see here that based on the analysis, Hatay seems to be a very much affected area, and then Adiyaman and Osmaniye. Something that we observe is that the province of Kahramanmaraş, which we know that had a lot of collapses, seems to have a very small percentage of red buildings. And this is something that we try to see why we get this result. And the explanation is quite easy. As I said again, this exposure model is a very coarse exposure model. So for Kahramanmaraş, all the buildings of the whole province are concentrated in this point, in the centroid of the Kahramanmaraş polygon. But if we take a look at the actual distribution of the population in Kahramanmaraş, we can see that the center of the city, which is around here, it is located around 13 kilometers from the fault, while this point, the centroid, is located 34 kilometers away from the fault. And this means that there is a significant deviation between this point and the actual location of the Kahramanmaraş city center. And this is something that is reflected in the results of the analysis. So, we also used a disaggregated exposure model, which resulted from the course one using population data. And we can see here that in this case, the Kahramanmaraş province has in fact a lot of more, a greater percentage of buildings that collapsed or had severe damage with respect to the more coarse province-based exposure model. I said earlier about the shake maps that they are updated a lot of times as new data become available. In the next slide, I will show an example of how the shake map for the first event evolved from the first version that was available 10 minutes after the event up to the last version. It goes a bit quickly, so please try to watch it from the beginning. So here we see the version as it gets updated, and we see how this is reflected on the shake map. I hope it will play again. Yes, we see that it starts from a single point, and as the information on the rupture is included, the shake map changes significantly. So, having this in mind, we try to see how much this evolution of the shake map affects our results. So, we have this kind of graph which shows for the different versions, so on the x-axis we have, let's say, time, and on the y-axis we have the number of buildings at each damage state. And what we observe is that around 4 days after the event, these results are stabilized. And this has to do with the fact that after 4 days, we had the incorporation of the fault rupture into the shake map, and this is something that stabilizes the results, and after that, the differences are very small. Another important information is that even with the first version, we are able to identify the severity of this event, even not with a very important accuracy. And finally, what we want eventually to do is compare our estimates with the actual observed damages. So these are the officially announced data for the whole study area. I'm sure that this data has changed by now. So we have around 1,700,000 buildings, and these two numbers, around 230,000 buildings, are the buildings that exhibited heavy damage or collapsed. So we can compare this number of buildings with the buildings that we have in our extensive and complete damage state. The results are compared here in terms of percentages because the total number of buildings is not the same in the analysis and in the official data. But what we see here is that the percentages are in very good agreement, even with the coarse exposure model, but even better with the disaggregated exposure model. The important thing is that all these open access datasets and models, it seems that we can use them for a first order rapid damage assessment at large scale, so that we have a first order estimate of the expected damages after a significant event. The effect of the shake map is minimized very soon, while the disaggregated exposure model results in a better agreement with the observed damages. Just one slide for the similar analysis we have done for Thessaloniki, for the 1978 earthquake, and for the Athens 99 earthquake. Here we compare the post-earthquake tagging, as Dimitris showed also in his presentation, with the results of our analysis. In some cases the agreement is good, in some cases the agreement is better. In any case, we can see that we have the tools to first verify our models and then to make some estimates for the impact of future earthquakes. Some final conclusions. I have said all this before. There are plenty open access datasets, models, and tools that we can use for the risk assessment of different types of structures. The comparison with observed data shows us that we can use them for a first order estimate, especially when we talk about large scale, but still there are a lot of uncertainties that we should address in the future so that we have more accurate estimates. One of them has to do, of course, with the site modeling, which, as I mentioned, is very rough in all these types of analysis that I presented. Thank you. That's all.